Everyone. Myself, Zakaria Ahmed, Laboratory Assistant Biotech Hub, Bahana College. Welcome you all here to our 3-day long uh, online hands-on training program on bioinformatics, which is organized by uh, Institutional Biotech Hub, Bahana College, Jorhat. Thank you. Now I like to request our Honorable Principal, Bahana College, Dr. Sumbit Chalia sir, to inaugurate the program. Thank you, sir.
Good afternoon, everyone.
Good afternoon, sir.
Am I audible?
Yes, sir.
Oh, yeah. Good afternoon, everyone. It gives me great pleasure to extend my warm and cordial welcome to all of you to this 3 days hands-on training session on bioinformatics. On behalf of Bahana College, I extend my heartfelt greetings to our distinguished resource person, researchers, respected colleagues, dear students, and all participants who have gathered here for this important academic event. Bioinformatics is one of the most dynamic and rapidly advancing fields of modern science, where biology meets computer science and data analysis. It has transformed the way we study genes, proteins, and biological systems, opening new possibilities in areas like drug discovery, genomics, and personalized medicine. We are truly privileged to have with us Dr. Rohan Meshram of Savitribai Phule University, who will be sharing insights on recent developments and applications of bioinformatics. I am sure that today's talk will broaden our understanding and inspire new ideas for research and innovation. I take this opportunity to thank the Institutional Biotech Hub of Bahana College for arranging this valuable session, and I once again welcome everyone present here. Let us look forward to an engaging and thought-provoking discussion ahead. Thank you and very good afternoon to all of you.
Thank you so much, sir, for inaugurating our program. Now I like to request our Honorable Vice Principal Ma'am, Dr. Pointa Borua Ma'am, to for the welcome address. Thank you, ma'am. Ma'am join na. Yes, ma'am.
Good afternoon to all of you. Respected. Am I audible?
Yes, ma'am.
Good afternoon to all of you. Respected Principal Sir, distinguished guests, and esteemed participants from different colleges and institutions, and my colleagues and the convener of Institutional Biotech Hub and the different members of Biotech Hub of Bahana College, and my dear students, friends. Institutional Biotech Hub have arranged different programs from time to time for the greater interest of the students, researchers, scholars, etc. Today I feel proud that the Biotech Hub Bahana College organizes a 3-day hands-on training on bioinformatics. Now, you are all welcome to this program, and I hope from this program the participant will be benefited. I wish the program will be a successful one, and at the all the participants will be benefited from the valuable discussions and hand-on training on bioinformatics by the different resource person. A very special welcome to our resource person, Dr. Rohan Mushroom, Assistant Professor of Pune University, Bioinformatics Center, for his interest in improving quality of our participant in the field of molecular dynamics and stimulation. I think all the participants will be benefited from this topic and know about the application in different fields. I welcome you all again and thank you all. Thank you.
Thank you so much, ma'am, for your speech. Now I request our coordinator, ma'am, Dr. Sangeeta Das, ma'am, to say a few words to you, ma'am. Thank you, ma'am.
Very good afternoon to one and all present here. Respected
Thank you, ma'am. Now, Miss Mallika Bora, Laboratory Assistant Biotech Hub, will introduce our resource person. Thank you to Miss Mallika Bora.
It is my honor to introduce Dr. Rohan Dhanarjan sir, an accomplished academician and researcher in the field of bioinformatics. Dr. Meshram currently serves as Assistant Professor at the Bioinformatics Center, Sadekpura, Pune University, where he has been instrumental in advancing both teaching and research in computational biology and drug discovery. With over 14 years of teaching experience as a PhD in bioinformatics, Dr. Meshram works research the gap between biology and computation. His research focuses on applied and developmental bioinformatics, particularly in molecular modeling, molecular dynamics, simulation, and computer-aided drug design. He has published over 50 international research papers, with his work appearing in reputed journals such as Biochemica and Biophysical Extra, Medicine, Journal of Molecular Lipids, and Scientific Reports. His research contributions have earned him an H. Index of 18 and over 1,300 citations. Beyond academic publications, Dr. Meshram has demonstrated a remarkable commitment to innovation. He has developed several bioinformatics tools and databases, including Growing, a Windows of GeoMate, BeFair, a DMD plugin for free energy estimation, NAMD Automator, a graphical user interface pipeline for automating MD simulation workflows, and FilterBase and TurboDB. Chemical and flavonoid databases access across more than 70 countries. This software Growing alone has crossed 1,900 downloads from 76 countries, making complex molecular dynamics simulations accessible to researchers worldwide. We will also file multiple patents in software copyright, including two granted international patents from South Africa, underscoring the transnational approach to research. These ongoing projects are supported by prestigious national agencies such as BDPDS and SCRB, and he is the investigator on major grants worth several crores under the DIC, DSTFT, and ANRF fair scheme. Dr. National Outreach extends to pedagogy and scientific communication. He runs an educational YouTube channel, Scribbles in Bioinformatics, widely followed by students and researchers for training in computational tools. He is also a South Africa resource person and invited speaker, having delivered lectures across India on topics ranging from molecular simulation and drug discovery to bioinformatics applications in life sciences. Please join me in welcoming Dr. Rohan Mehta, a visionary educator, innovative software developer, and an inspiring researcher who continues to make bioinformatics more inclusive, accessible, and impactful for the global scientific community. Thank you.
Thank you, Ms. Malika, for introducing our resource person. Now, I like to request today's resource person, Dr. Rohan Meshram sir, to start the session. Thank you, sir. Now, I like to hand over the session to you. This session is all yours, sir. Thank you, sir.
Thank you, Malika, for your kind words, and I really don't know if I deserve everything that you have said. But anyway, thank you for your kind introduction. And so to begin with, today I am going to demonstrate you what is molecular dynamics and simulation. So the main objective of today's session is to give you something that will get you up and started if you want to get into this field. So this being only a 2-hour session, and I have limited time, so I will go through very basic things on what are the basic concepts behind MD simulation, so that you will get to know as to what is exactly that is happening in the background. So first we will deal with that. We would get an elementary idea of what exactly we do when we say that we are performing MD simulations, and then I will demonstrate you how do you set up and run MD simulations of a simple protein ligand complex, and if time permits we will perform some elementary analysis of the resulting data. So the thing is that MD simulations are quite computationally intensive and they will take some time. So I will tell you as to how is that you set up the simulation, how is that you run the simulation, and we will directly jump to the results, right? Because usually the simulation extends from days to even weeks, depending on what computational power you have with you and what is the size of your system. So I will tell you how is that you set up the system, how is that you initiate the simulation. Okay, and then we will stop, and after the simulation completes, whatever the situation is, we would again begin the analysis, so that you would get a kind of overall bird's eye view as to what exactly happens when you perform MD simulations. Okay, so let me first now I hope that everyone is aware what is that is going to happen in the next 1 or 2 hours. Okay, so please pardon me if you think that I am going a little bit fast or everything is not covered. So for that purpose, if you think that you have lost somewhere or you are not following this thing, then you can follow my YouTube channel. There is a complete playlist. Am I allowed to share my screen, suppose.
Yes, sir.
Okay. Okay, now is my screen visible?
Yes, sir. It's visible.
I hope it is.
Yes, sir.
Okay, so if you go to YouTube and or on Google, if you simply search like scribbles in bioinformatics, the very first link that you would end up will be my YouTube channel. Okay, just wait for a while till it loads up everything. Okay, so this is my YouTube channel, and if you are new or if you have not already subscribed it, then I would advise you that you please subscribe this channel so that every time I upload something, the new content will be available to you. So if you get lost somewhere in today's session, you can go to this playlist option, and there is entire playlist of like practicals in MD simulation, wherein I have used Hindi as well as English language. And
imagine conducting every part of your research.
Here is, you can say, playlist of 5 days of my workshop. So I am going to cover a few of things from this playlist. Okay, so now you know, okay, if I do not follow anything, where is that I'm supposed to look into later on, if you want to go into more details. Okay. So fine, let me now first begin with explaining like what is MD simulation. Okay, so to introduce you guys with the concept of MD simulation, let me first tell you, or let me first brief you as to what exactly happens when you end up with analyzing the protein ligand interactions, because that is where most of the MD simulation application is given into, right? So MD simulations are most probably and most popularly used in the field of drug discovery, wherein you try to have a temporal look on how the newly synthesized inhibitor molecule might behave in the binding site of the protein. So if you guys have kind of followed me in my previous lecture at Bhavna College, last time when we met, I demonstrated you how do you look into the protein ligand interactions and how is that you perform structural analysis. So let us begin with the same thing over here. So in today's session, what we are going to do is that we are going to deal with the MD simulation aspect of a viral protein called as NSP3 macrodomain that is in complex with, say, some pyrozoline inhibitor. So the thing is that whatever I am going to show you today, we have already published it in a research paper. I'm showing you this research paper so that you can get into more details of what is that we are doing today. So this is the paper where we have published the data that I am going to discuss with you guys today. Okay, so this is where you are supposed to look if something goes wrong in, or if you want to get into more details of the system as such. Okay, so now let us first talk about what exactly is MD simulation, right? So MD simulation usually begins with like if you have a protein ligand complex, like I will show you, maybe that will create more visual representation so that you can appreciate what exactly I'm talking about. So this is a simple SPDB visualizer. This is, of course, a free software. You can download it. And what I have loaded now is a structure of my protein called as SARS-CoV-2 NSP3 macrodomain, and that is in complex with, say, some inhibitor. This is the pyrazoline inhibitor that one of my collaborator had synthesized, and she was interested in performing MD simulation. So after performing molecular docking, or even if you download such a structure from PDB, this is usually the starting point of getting into MD simulation, right? So MD simulation की शुरुआत यही से होती है. Either you can have results from molecular docking, wherein you might have docked some newly synthesized compounds, or you can use, say, some phytochemicals, and you might have seen interaction with, say, some therapeutic protein, right? Or you can begin MD simulation with the already co-crystallized experimental structure from PDB that you can download. But for sake of simplicity, in today's demonstration, we will be using this system of some pyrazoline inhibitor that you see over here. It is triaryl derivative of pyrazoline, and this is a small micro domain of SARS-CoV-2 NSP3 domain as such. Okay, so I have deliberately selected this small protein so that you can also complete the simulation in 1 or 2 days, or maybe in a single day calculation. Okay, so this is a small protein that is only 169 amino acid residues, and you can, do it in a single go. It won't take much time, even if you have normal PC or normal laptop as well. Okay, one more thing that I would like to say is that whatever software that I am going to demonstrate you are all open access software. You can download them easily from the respective websites, and you can start out working right away using those software. So it is not like I am demonstrating with you to you with some commercial software that won't be available for you to practice and exercise, right? So in this session, we will be using program called as NAMD to compute the trajectories, or what we call it as to perform MD simulation, and we would be using VMD, which is again open source program that you can download from their website. And this VMD will be used for setting up the system and for analysis of the results. So this is what it is, guys. It is going to be a fun session. No need to get into intimidation, like how is that things are going to roll out. Okay, so it kind of initially seems to be a very complex thing to do, but if you get used to these things, for me now it has become quite an easier task. The more you practice, the more you would get into details of how do we set up things, and how is that we proceed for simulation. So I would advise you that whatever I show you today, and whatever I have already shared on YouTube, that will definitely benefit you to start at least with MD simulation, to begin somewhere, right? Okay, so let us first talk about today what are MD simulation at the very first place. Okay, so generally when you download any structure from PDB, right? So this is what you might get. This is how the PDB structure might look like, right? Or when you perform molecular docking, you would end up with various poses of your ligand in the binding site of your protein. But my friends, when it really comes to doing things practically, at such condition, when you isolate those protein, or when you perform those assay, these protein ligand complexes are no longer static, right? Why? Because most of the biological macromolecules, they entails motion in them. They are always in the state of dynamics. They are always moving, and it's motion that will actually impart its functionality or its catalysis or its inhibition if you are talking about proteins, right? So the thing is that you should first know and appreciate that the proteins, that model that you either create by homology modeling, or you download it from PDB, or you obtain protein ligand complexes using Autodoc or any docking software. They are not static. They are always in the state of motion. And my friend, if you rely only on molecular docking for obtaining the interactions and evaluating the energetics of your protein ligand complex, then you are missing this entire scheme of motion, right? You are you would be completely ignoring the fact that the target protein that you are dealing with will be always in the state of motion, and that would impart the stability of your protein ligand complex, and that would eventually shape up the inhibition assay or your activity of the small ligand that you might have designed. So now, is it possible by a computational technique to model this motion in the proteins? And the answer is yes, my friend. That is what molecular dynamics simulation does. So in molecular dynamics simulation, what we do is that we try to model this motion in the protein ligand complexes or protein complexes that you might have downloaded from PDB. Okay. One more thing that I would like to mention is that when you perform molecular docking, you perform everything in vacuum, right? So you remove out all water molecules if there are any, and you perform molecular docking on the protein ligand system in vacuum condition. But when you perform the assay, the proteins are always in aqueous conditions, right? And in cells as well, they are always in aqueous condition. That means they are already surrounded by water molecule, and thus in molecular docking you are completely ignoring the contribution of water in estimating the free energies of your protein ligand complexes. So yes, anyone want to ask? Okay, Paushali. Okay, fine. So this is what we try to model, right? That is what I wanted to say. That when you perform MD simulation, we try to model the motion that is involved in your protein, as well as the solvation effect is also taken into consideration when we perform MD simulations. Okay, so before I get into telling you like how is that this MD simulation is done, let me directly first show you what is that our endpoint is, so that you would then appreciate how things are going to happen in this session. Okay, so this is the static picture that I have been talking about. Now let me show you the results of MD simulation so that you can get how is that the molecule moves in the computer, or how is that we model the motion in the computational setting. Okay, how to do so? Let me show you directly the results. Maybe where we for visualizing, as I have already told you, we will be using this software called as VMD. and you can download this VMD for free. Okay. All you have to do is to registration. Registration is also free on the University of Illinois website, and you can download it. Or most probably you might already have installed it on your PC. Now, for visualization purpose, you need to first load the PSF file. I am going to tell you in more detail as to what are the PSF file, and once you have loaded the PSF file, you can load the trajectory data. When you perform MD simulation or any simulation as such, you would end up with trajectory, right? And I am loading this trajectory, and this trajectory will contain frames. So when I say load, when I click this load button, you will see that the number of frames will start to update over in this column. Right? Now you can see that what you are visualizing now is the trajectory of the same protein that I have shown you, protein ligand complex. Now you can see that the protein ligand complex is in, I have solvated it in a water box, as you can see. These are small V-shape are these water molecules, wherein the red dot indicates that this is an oxygen and the white dot indicates that this is hydrogen. And this centrally placed blue colored or green colored thing that you see is your protein ligand. So that is how, my friends, what you are visualizing now is the trajectory of a protein ligand complex solvated in a water box, and the trajectory that you are seeing is for let me see. The trajectory that you are currently seeing. That is about, really don't remember how long I have run this simulation for. This is 1 nanosecond simulation. Okay. I have, for the sake of simplicity and for the sake of your ease of completing that tutorial, I have created the trajectory only for 1 nanosecond. But my friends, when you actually perform in this simulation and you intend to publish it in some good quality journal, then it is advised that you at least perform simulation of 100 nanoseconds. Right? तो यहाँ पर जो मैं बता रहा हूँ वो सिर्फ 1 nanosecond है. So you play this, if you push this play forward button, and maybe you can scroll down the speed of the trajectory. So what you see is that one after another, the frames in your trajectories are displayed. This is frame number 1, 2, 3, and 4. So in this way, you can say that the trajectory contains frames. Okay, and each and every frame that you see over here corresponds to the state of the system after every 100 picoseconds. Okay. So what you see is that how my system will look like after every 100 picoseconds. Okay. So each and every frame corresponds to the state of my protein ligand system solvated in water after every 100 picoseconds. So in this way, if I increase the speed, now you can see that the protein is loaded. Okay. So let me show you more details of how is that the protein ligand moves as well. For doing that, you might have to create representations. This is how we usually work in VMD. We create representation of whatever we want to visualize. That is how it's working. So what we would want to see from the trajectory is that we would want to focus on protein, and in the selection tab, you can select this protein and use this create representation button, and that will create a representation for OP2. Now, if I delete this previous by default whatever we have loaded, now you can only focus on OP2. Okay. Now our system also contains the ligand, right? And I know the name of my ligand in my system is with name link. So I will go to this selection and with this keyword option, I will select residue name. It will populate with whatever number of residues are there in your trajectory, and I would double click on this name of residue ligand, and everything would appear over here. And when I click this create representation button, it has created another representation for ligand. Okay. So now let us visualize our protein in a more familiar way that you might have been already looked into in biochemistry book. In ribbon representation, you can see the protein is in ribbon representation, and let us visualize our ligand in maybe CPK so that things appear more clear to you. And now let us see how our ligand has adjusted itself into the binding site of the protein. And when I click this play button, now you can see that the protein ligand complex has started to move, and this is how your ligand and protein will interact in time, and we have modeled the motion, and you can see that the aryl group is arranging itself by orienting some functional group. That is how usually things happen in cells, right? The protein ligand always the protein ligand complex is kind of always in state of motion, wherein it tries different conformation, and every time it moves, some interactions are formed. Every time it moves, some interactions are lost. Therefore, new hydrogen bonds or new interactions can be explored and monitored. So, my friends, I hope that now you get a clear-cut idea as to what exactly is that we are dealing with. तो सबकी समझ में आई होप आ रहा होगा कि एमडी सिमुलेशन क्या है. ओके, इज एवरीथिंग ओके, फाइन? यहाँ तक समझ में आ रहा है सब लोगों को? आई होप आई हैव मेड इट क्लियर. So now our objective is how is that we set up such MD simulation, how is that we execute those MD simulation, what softwares that we use, what are the various methods that we are going to use. वो सारी चीजें मैं आपको भी बताऊंगा. That is what we are going to do. Okay, I hope this is the question time. I will give pause for a while for you to give a chance if you have any questions or any doubts कि भाई समझा नहीं. Okay, no, so if there is no any doubts, I will proceed further. Okay, fine. I hope everyone is with me, and I hope that we would finish things in time. Okay, so now let us begin on addressing the question like how is that we set up the MD simulation, right? So to begin with, what we usually do is that I will now show you how is that. Let me close this thing. We will come to this thing in a while when we analyze the data. Okay, so I have created this folder called as test, and in this test folder I have already tried doing this for practice in today's morning itself. So I will just delete the data. Okay, so usually you begin with something like this, the protein ligand complex of your system, right, wherein you have the protein and you have the ligand in it. So when we perform MD simulation, what we usually do is that we need the protein and ligand in separate files. Okay, so that we can assign them segments. So when we perform MD simulation in NAMD, it is always advised that you have different segments that you assign to each and every component in your protein or whatever your system is, right? So in our system, let us give segment name B to our protein molecule, or we can say let us kind of represent our protein molecule in form of a segment, one segment, and let us represent our ligand in another segment. Okay, so doing so, we will have to now separate the protein and the ligand complexes. Okay, and separation is quite really very easy. What you have to do is to just select the entire chain. The red when you select the entire chain, things would become red in SPDB, right? And now what you will do is that once everything is selected, then you would go to this file and then save, and then selected residue of current layer. And I will name it with say some name. Let me name it as this APO. Let us rename it as APO. APO, why? Because it don't contain any ligand or any other information. The protein will be in its APO form. And when you click this save button, the only selected residue will be saved in a separate file, right? So I have already done it, so I will not do it again. And once you have saved it separately, then maybe we will again select this ligand molecule simply by clicking it, and then do the same thing, go to file and then save, and then selected residue of current layer, right? And we would again save it in a separate file, what we call it as ligand 3. Let us rename it as ligand 3 and hit this save button. So in this way, you will separate the protein and ligand into two separate files. Let me now load it and show you. Let me first now load the protein molecule. As you can see over here, at the end of your list of amino acid residue, there is no ligand. It was there in the previous complex. And now you can simply drag and drop this ligand molecule. And if you press this Control and Tab on your keyboard, you can see that here is the ligand that we have loaded. And if I again push this Control Tab, you can see that the two molecules are being loaded as a separate layer in SPDB, right? So although you can see in this alignment window, or you can say in layer infos, you can visualize both at the same time, right? This is your ligand and this is your protein. Although they look like complex, but still they are loaded in two separate layers. So these are two separate things, right? So in this way, my friends, what we have done is that we have separated the protein and ligand. This is really very important. So whatever segment that you want to make in your simulation, you would have to separate them accordingly. Okay, so in our case, there would be only two segments, one segment for ligand and another segment for protein. Okay. Next thing that you need to do is that you need to create the PDB PSF pair. So this is, you can say, the starting point of getting into MD simulations. So this is one of the most important, you can say, input that is necessarily needed to be generated when you begin creating the system for your protein ligand complexes as such. Okay, so how is that we do that? So before I tell you what is this PDB PSF pair, okay, let it be. We will start out with the demonstration on as to how is that we create that PDB PSF pair, right? Okay, so what we have done so far is that we have separated the protein and we have separated the ligand. Okay, and another input that you might need is that once you have separated this ligand, you want to obtain something called as the parameters and topologies for your ligand, right? So once you have separated it, you will go to this another website called as SwissParam, and from this SwissParam you can generate the topologies and parameters for your ligand molecule, right? This is a simple form wherein you will have to upload the ligand molecule in this MOL2 format. You would have to convert that PDB format file into MOL2 format file, browse it and submit the query. And once you submit it, you would get the topologies and parameters of that topologies and parameter. This is the topology file of your ligand. You would definitely need this topology file for generating the PDB PSF pair. And the topology file for your protein will be inferred from this top all 27 protein NA topology file. So in order to create the PDB PSF pair, what is necessary are the topologies of the components that are there in your system, right? So what do exactly I mean when I say that we need topologies? So topologies, the thing is that your MD simulation program needs to know as to how the atoms in your system or in your protein ligand systems are connected to each other. And in order to create that thing, we need to have this topology and topology fields. Okay, so it is necessary that before you begin creating the PDB PSF pair, you should have topologies for your protein as well as your ligand. For the sake of simplicity, in this presentation, I have already obtained it and from this SwissParam server. Okay. Okay. So now we have the PDB file for your protein. We have the PDB file for your ligand. We have the topology for your ligand, and we have the topology for your protein. Okay. So now, having this with you, you are ready to roll with generating the PDB PSF pair, right? So there is a script called as this PSF gen script. PSF gen stand for PSF generation script. So I have already written this script. I will tell you as to what this script does. If you open it in any text editor, I am using Notepad++. It is also a free software. You can even open it in Notepad, whatever text editor that you have. Okay. So over here, you would have to tell like how many topology files are there. Right? This is the topology file that will be used for your protein. This is the topology file that will be used for your ligand. And we will be creating the segment with name B for the apo form of our protein. That is the protein that we have simply separated a few moment while, right? And we would be using this apo nsp3 pdb file. And then we would connect it with the name of the segment over here, and the next segment we will name it as ligand. For this segment we would be using the separated file ligand3 that we have generated. Okay, and after the script is generated, it will create a PDB PSF pair in form of two files, complex.psf and complex.pdb. So when you will perform by yourself, you have the feasibility to change the topology file it would be completely dependent on what type of force field you are using. I am using CharMem force field, specifically CharMem 27 force field. So I am using, I have written it appropriately. If you are using some another force field, Amber force field, or maybe some other thing, then you might take the respective parameter and topology files as such. Okay, so once we have this thing in place, properly written, all you have to do now is to load your VMD. Okay, now once the VMD is loaded, the next thing that you are supposed to do is to change the working directory. By default, when the VMD is loaded, it is the working directory is somewhere there in, I will show you. Currently, when it is loaded, you are here, program files x86, then University of Illinois, and then VMD. So this is the working directory, my friend. Okay, and if I give this list out command, you can see that there are all the files that are there. Okay, so now what you need to do is that you need to change the working directory from the default working directory to the place where you have all your inputs. Okay, so all of my inputs are there on this folder called as test, which is saved in my desktop. Desktop के ऊपर में जोरत नाम का folder है, and then there is a folder called as simulation, and then there is a folder called as test, and in this test folder I have all these input files. So what the software is, it is somewhere over here in C drive, program files x86, and somewhere over there. And our input data is somewhere on desktop. So we need our VMD to get data at the right place. Okay, so we need to change the working directory. For that, what you can do is that you can use this cd ... command to get out of the working directory. Okay, when you give this like cd ... that means you are going one directory up. So now you are in University of Illinois, as you can see. Okay, if you again give this command cd ... now you would be in program files x86. It is just like going into program files x86, right? Again, if you will give cd ... now you are in the main directory. Now you are in C drive. Okay, so to give you a kind of perspective, although we are saving everything on this desktop folder, the original location of this desktop folder is in C drive, as you can see. Okay, if you simply click over here, you can see the exact location of your C drive. What I will do is that I will copy this thing. This is the exact location where your desktop and everything is located in your computer. Okay, so now I will copy this thing and I will simply give the command see the directory and then paste it over here. The thing is that this VMD takes backslashes instead of front slashes. So you would have to change every time you get into the working directory by changing the slash pattern. Okay. So now what we are telling our VMD is that go to the folder in user, it will have folder name Rohan_admin, it will have folder name desktop, then it will have folder name Jorhat, then it will have folder name simulation, and then there will be a folder called as test wherein all our input files are located. And just hit enter. Now you can see that you are in the right folder. Okay. So in order to make sure that you are in the right folder, again you can give this list command and you can just correlate. Okay, all the files that are required are always here. Okay, so now you are in right location. Now, do you remember that the PSF Jane file that I have mentioned you that is used for creating the PDB PSF pair? All you have to do is to use this source command. Source command will tell your VMD that it is sourcing some script, and whatever commands are there in your script that would be executed in background, and it will create the PDB PSF pair with name complex.psf and complex.pdb. Okay, all you have to do is to give this keyword source and then the name of the script file where all commands are there. The name of the file is psfgen.pgm, and when I hit enter, now you can see, my friends, it has created a PDB PSF pair. Initially, the two entities were different, protein and ligand were in different file, but now we have created a complex, and along with this PDB file, it has created this PSF file, right? So now let me tell you what exactly is it in this PDB PSF pair. Okay, so your PDB file, of course, it will have data on the coordinate of each and every atom. Okay, so this is nitrogen and its respective XYZ coordinate. The second one is hydrogen that is attached to nitrogen and its XYZ coordinate. So this will give location of each and every atom in your protein ligand system, right? And again, if you open this PSF in any text editor, it will tell you, okay, you have got segment name lig and segment name B. This segment B, as you can see over here, contains all the information of your protein, and this segment lig, it contains all the information of your ligand, as you can see over here, ligand, right? So along with this thing, what it does is that it will have something called as atom typing information, and this atom typing will connect your topologies to the parameters that we are going to use in our force field, right? So this file will actually have the information like what are the bonds, how are the atoms connected to each other, how the atoms are connected to each other, how the angles are there in your bond, how are the dihedral angles that are there, right? So it will give you the idea of connectivity, and this PDB file will give you the idea of the atomic positions. Okay, so now when we perform MD simulation, all the software need to do is to predict the position of new atom. It will kind of predict the coordinate of new positions when our protein will propagate in time. Okay, so now let me kind of show you once we have created successfully this PDB PSF pair, and mind my friends, this is the most critical step. If something goes wrong here, nothing will work later on. So I have already standardized this thing, and it appears that things have gone quite really very smoothly over here. But this is where this is the bottleneck of the entire simulation process, you can say. Okay, so now once we have created it, what you are supposed to do now is to simply load it in VMD by double clicking it, and then you can right click it and load data into molecule. Simply use this browse button and load this complex.pdb file, its pair, and load it. Now you can see that we have the PDB PSF pair of your protein ligand complex. Okay, so abhi ye cheez ho gayi. Okay, now what we need to do is that we need to place this protein ligand complex into a water box. That is what I have shown you, right? So ye karne ke liye, to do this, we will be using the solvation module that is there in your VMD. Okay, तो इसके कमांड भी मैंने यहाँ पर आपको I have already written this command. I will tell you how is that you use it, right? So for that, for solvating our protein, we would use a package called as solvate, right? And to import any package, there is the command that you are supposed to give. The command is like package require solvate. This command will import a package name 1.6, which is a solvate package. So when you see that some number appears over here after you give the package command, that means that particular package has been successfully imported in your working environment. Okay, fine. Now what I will give is that once the package is loaded, I will simply copy this command and paste it over here, right? So what do this command mean? So this command says ki like we need to solvate these two files, complex.psf and complex.pdb. This dash t will tell ki how far your solvation box will go, right? So if this is the farthermost atom in your protein, then this 5 indicate that a solvation box that would extend to 5 angstrom from the farthest atom will be created. Okay, and this dash O indicates that what will be the name of the resulting PDB-PSF pair of the solvated system. So we would be creating another PDB-PSF pair, but now this time it will contain the protein ligand complex along with the water molecule, and we will name it as complex_WB. WB stand for water box, right? So once you either copy paste it or write it over here without making any mistake, of course, all you have to do is to hit enter and something will happen. And now you can see that the PDB-PSF pair has been completed. So always have a look at over here, right? Solvate completed successfully. That means we are done. Okay, you can straight away give exit command over here, right? And as you can see, the newly created water box molecule is here now. Well, now let us load this water box. As usual, first we need to load the PSF file. Once you load the PSF file, click on the first top layer, then right click, load data into molecule, then go to this browse, okay? And what is the name of its corresponding PDB file? It is complex_WB. Select it, open it and load it. Now my friends, you can see that we have created this PDB-PSF pair of a protein which is now solvated in a water box. Okay, one more thing that is needed to be done over here is that we would have to balance the charges as well. So usually what happens is that it is entirely possible that when you begin with simulation, there might be some positively, the system may not be quite balanced in terms of charges. Okay, so here we have an opportunity to balance those charges so that we can make our system neutral. If there are excess of negative charge, then maybe we can balance that negative charge by adding the counter ions, positively charged ion, Na+ ions can be added. Or if there are more of the positive charges, then chloride negative ions can be added. Okay, so how is that we do that? Okay, so this is called as charge neutralization. It is another step. Okay, so how is that we now neutralize? To neutralize your system, okay, all you have to do is to go to this extension and go to this modeling, and there is a section called as add ions, right? Simply go to this add ions. A new dialog box will appear with the name auto ionize, and what it will do is that it will neutralize your system using this NaCl. Okay, it would calculate what are, if there is unbalance in charges, and whatever unbalance is, it will replace some water molecules with the respective ions, and hence your system will be neutralized. Okay, so what you have to do is to hit this ionize button, auto ionize button, and it will create two files called as ionize.psf and ionize.pdb. Now you can see these files are not here. Okay, so once we kind of balance the charges, it will create two more files, two more PDB PSF. One with ionize.psf and another with ionize.pdb. Okay, now you can see that it has again created two files, ionize.pdb file and its pair ionize.psf file. Okay, so now let us close this thing and load this ionize.psf and let us load the ionize.pdb file. Okay, now this system was actually not it did contain any misbalanced charges, so nothing was added, but whenever if there are charges, it will kind of show okay, we have replaced this much amount of chloride ions, and we have added this much amount of sodium ions, so on and so forth. So it is usually advised that you begin with PDB PSF pair, then you solvate it, and then auto ionize it, so that now you are ready for generating or for simulating your system. Okay, so before we get into more details, one more thing that you would need is that you will need some information of this water box that we have created. Okay, you for effective simulation, you would need what is the exact location of the center of this box. For implementing periodic boundary condition, you would need something called as the cell basis vector value that are usually calculated based on the dimension of this box. Okay, so let us not go into more details of like what is periodic boundary condition and everything. You can watch my video wherein I have already demonstrated you. We are already running out of time, so I will just demonstrate you what values are needed and how is that you calculate those values in practical point of view. Okay, so what we will need is a script that of course I have written. Oh, it is already there. This is the script that I have already written. It is written in Python. Sorry, it is written in TCL. Why? Because VMD understands TCL language, right? So what this script will do is that it will calculate the values for cell basis vector, and it will calculate the values for cell origin that are essentially required for setting up any MD simulation. And if you are using particle mesh evolved that we are using, उसके भी grid size अपने को लगने वाले हैं. So that eventually will be calculated using this script. Don't go into more details of this. It might seem kind of technical jargon. I won't go into more details. I will tell you as to how do you use this script. Okay, fine. So Now, how is that we calculate those values? For setting up the periodic boundary condition, for knowing the coordinates for particle mesh Edwall, and for knowing the coordinates of the center of box of your system. Okay. For that, you need to go to TK console. Make sure that you are there in the working directory always. If you are not in working directory, then you can use this CD command and go to the working directory and then start working. Okay. So the thing is that always make sure that you are in the right folder before you give any command. That will help you a lot of painstaking errors, right? Okay, fine. So once we have this file, this PBCPME calculator script, and we have loaded everything in our VMD, the PDBPSF pair, and we are in the right working directory. Let us list out if this PBCPME calculator.tcl file is available here. Yes, it is there. All you have to do now is to give the source command. So whenever you want to run something, it can be run using this source command. So once you write this source, it becomes green. That means your system is ready for taking the input file. So what we are doing now by giving this source and name of file is that we are telling this VMD to source whatever the program that I have written in this PBCPME calculator.tcl file. Okay, and all you have to do is to hit enter. It will calculate everything and it will write a file called as PBCPME gridsize.txt that it has recently generated. You can open it in a text editor and you can see that it has calculated the grid size of your particle mesh Ewald. It has already calculated the cell basis vector that will help you to set up the periodic boundary condition in your simulation, and it has calculated the cell origin. So where is that we are going to need this? I will tell you in a while now. Okay, so once you have this thing, just copy this output file, and now let us begin with getting your simulation done. Okay, so what usually happens is that we have the ionized.psf file and ionized.pdb file that we have recently generated that is needed to be there in your working directory. We have the parameter file for our ligand molecule and we have the parameter file for our protein molecule, right? So make sure that you use the corresponding parameter. जैसे कि ये ionized.psf and ionized.pdb are pairs. In the same way, the parameters and topologies for a force field are always in pair. So if you are using Charmim 27 force field, then make sure that you are using the corresponding parameter files. Okay, so to make it more clear, maybe if it is still there, I will show you. Okay, while generating the PDBPSF pair, we have used this top all 27 protein and nucleic acid topology file. Its corresponding parameter file will have similar names, right? So this is the corresponding parameter file for the topology file. We have used ligand3.rtf as a topology file. We are using ligand3.drm as a parameter file. So this parameter file will connect the atom typing information with the force field. That is what it is. Okay. So now to begin the simulation, what is necessary is that you need to have the PDBPSF pair. You need to have all the parameters that are there for your system. तो ये चीजें रहना जरूरी है. Now, how is that we proceed with the simulation now? So, when we say that we are performing MD simulation, we eventually perform something called as the conventional molecular dynamics simulation, wherein what you do is that you begin with minimization of your system, right? So, why is that we need to do minimization? is that we have added the water molecules around our protein ligand complex, right? So it might happen that VMD might place some water molecule in very vicinity of your protein ligand system, and that might create steric clashes, right? So it is entirely possible. So by generating or by proceeding with energy minimization, what you make sure is that your system is not sterically constrained. So what you do is that you reorient those water molecules if they are forming any clashes. So the objective of performing energy minimization over here is not to obtain the global minima of your protein ligand system, but to ensure that there are no steric clashes between your protein and water molecule that you have simply added over here. That is the main objective. Okay, so after you perform energy minimization, then you proceed for something called as heating. Okay, this is another process that we usually do after energy minimization. Okay, so in this heating, what you do is that you gradually and very slowly increase the temperature of your system from 0 to 300 or 310 kelvins. Why? Because 300 is the physiological temperature, I suppose. You guys are from biology background, so you are well aware of this biochemistry stuff. So when we perform minimization, it is assumed that we are doing it at 0 Kelvin, and in order to bring our system to near physiological condition, it is necessary for us to increase the temperature very gradually, and this is done in the process of heating. Okay, so once your heating is completed, another step is there. It is something called as equilibration. Okay, so why is that we need to perform this equilibration, and what exactly happens in equilibration? So equilibration means what we do is that we try to level off the potential and kinetic energy that might have been disturbed in the previous heating stage, right? So when we heat our system, when we gradually increase the temperature, the kinetic energy might be pumped into your system. So it needs to be kind of leveled off by balancing it with the potential energy, so that your system would be thermodynamically stable. Okay, so that is why, my friends, we do equilibration. It is very important step, and once your system is equilibrated, then we proceed for something called as production run. And in this production run, you run your simulation for say some 1 nanosecond, 100 nanosecond, whatever you wish, and from there you obtain the structural data for your analysis. Why is that we call it as production run? The answer is simple, that we collect the data from that simulation, therefore we call it as production run. Okay, so now I hope that you people are familiar with the procedure. First we need to perform minimization. Next we need to perform heating. Followed by heating, we need to conduct equilibration, and after equilibration we need to proceed for production. Okay, so now how is that we do this thing practically? So practically, when you run any simulation, right, so whatever things that we were doing in VMD, I mean for time being. Okay, but once everything is ready, we will conduct our simulation in another software called as NAMD, right? So NAMD is the software that will eventually calculate the trajectories that you have seen, the beautiful trajectory that I have shown you. It is calculated using NAMD. So how is that you obtain this NAMD? NAMD can be simply obtained, just type NAMD in Google, and you would be carried to this University of Illinois website, and you can download it from over here. It will ask you for registration, but the registration is free. You can download it from its website. Okay, so once you have downloaded it, it will be somewhere like in a zip file maybe, right? And I will maybe show you how is that it will look. It will be something like this, NAMD, the name of version and multi-core thing. It will be a kind of zip file. All you have to do is to unzip this thing, extract, and extract to this thing. It will create a file called as NAMD multi-core. Simply copy this file and paste it in your C drive. This is very important, right? You should paste it in C drive. Once you paste it in C drive, then maybe you would rename it and remove this multi-core thing and let it be simply an NAMD. I have already done this thing, so I will not do it once more, right? So this is how you install NAMD. Very simple, my friends. Okay, so once NAMD is there in your C drive, just open it. This is the program that we will be running in the background. This is the program that will calculate your trajectories. Okay, so let me close this thing. Things have already become messier. Okay, now how is that this NAMD program knows how is that simulation is needed to be executed? For that, you would require for each stage all the information that is required to run your simulation is there in this configuration file. So what we do is that we construct this configuration file. It is a text file, of course, and if you open it in any text editor, all the commands that are there that are required for executing your system that are there in this configuration file. So whatever information that is required by this NAMD program to execute the minimization simulation, it is supposed to be provided in the form of a configuration file. Like, let's say for example, it will need to know what is the structure file. Then we provide the structure information in PSF file that we have generated. So we need to tell, okay, the structure file is with name ionize.psf, the coordinate file is with name ionize.pdb. These are the force field parameters that we are using. Okay, and I would advise you that you don't change anything, right? So if you have multiple ligands, then there would be multiple parameter files. So it is not like it will only take 2 parameter lines. However, and whatever number of parameter files are there, you can populate it or list it over here. Okay. Then to tell you that we have calculated some values, right? PBC, PME, grid size. So these values are supposed to be populated in your configuration file. So that, well, say for example, you can see that this PME grid size 54, 50, 50, I have populated it over here. Cell basis vector 1, cell basis vector 2, cell basis vector 3. I have used this value in defining the periodic boundary condition. All you have to do is to copy and paste it over here. As you can see, these are the same values. And to initiate your simulation, your software will require the cell origin. These are the same coordinates that we have copied. So now you can kind of correlate whatever values that we have calculated, where are they supposed to be populated. Okay, so now let me tell you how minimization happens. Minimization usually happens in this step. Now step 6000 will tell you, okay, we will be minimizing our system using 6000 steps of conjugate gradient algorithm, or you can use steepest descent or whatever NMD uses. Okay, so I won't go into more details of this thing. Okay, so this is how your NAMD will perform the simulation. Okay, all the necessary information that is required to conduct the MD simulation is already there in this configuration file. So this is the configuration file for your minimization. Then I will show you the configuration file for your heating. So heating usually happens over here, right? MD protocol block. We will increase the temperature by 0.01 Kelvin at every time step, and therefore to reach the temperature of 300 Kelvin we would require this much number of steps to be calculated, right? So this would be a kind of 300 picosecond simulation, wherein we start with the initial temperature 0, increase the temperature by 0.01 Kelvin at every time step, and we run the simulation for this much time step and end up with the final temperature of 300 degree Kelvin. After that, let me show you how equilibration is done. Again, there is a configuration file for equilibration, and in this MD protocol block, equilibration is done using a computational technique called as rescaling the temperature. Okay, so let us not go into details of this thing, but this is where your you can say equilibration will happen. Okay? Rescale frequency will be at every time step, and rescale temperature will be at 300. Why? Because we have ended up with a temperature of 300. So this will eventually equilibrate your system. And finally, here is the production run. Okay. So we would be running this production in NPT ensemble by keeping the temperature and pressure constant. That is called as NPT. So in this case, I have used Langevin dynamics for controlling the pressure as well as controlling the temperature. Again, we have used the Langevin dynamics. So these lines will control the temperature at 300 degrees centigrade, 300 Kelvin, sorry, and the pressure will be maintained at 1 atmospheric bar. Okay. So my friend, once you do this thing, once you have all the production file, all the configuration file ready, now it's time for you to execute the simulation. Okay. And to execute the simulation, all you have to do is to get to this, get to the location, get to the, you can say, the address of your current directory, and simply click it over here and give the command cmd and hit enter, right? So doing this, it will directly load the command prompt in the working directory. Okay, so now what we need to do, once you are in working directory, you can use this dir command just to make sure that everything that is required for executing your simulation is there. It is there. Okay, so all the NAMD software, and as I have already told you that we have installed or we have located this NAMD software in our C drive. What we will do, we will go to the C drive where we have pasted that NAMD. Okay, simply copy its path and paste it. So by doing this, what we are doing now is that we are telling you, okay, your NAMD software is there somewhere in C drive in folder name NAMD, and the name of the executable file is NAMD2, right? Because this is the program that we will be using for NAMD, for executing the simulations. Okay, fine. Now, once you have told your computer ki where exactly is your NAMD located, then you need to tell ki, okay, what is the name of your configuration file. First, we need to perform this minimization. So, to perform minimization, we will have to tell it, okay, NAMD2, how many processor we are supposed to use, right? So my PC contains 8 processor. So I will add this line plus P8. That will tell NAMD to use all the 8 processor in my PC. What is the name of the configuration file? min.coma, and everything that will happen in my simulation, that will be saved in a log file called as min.log. Right. So this command kind of tells you, okay, this use this NAMD that is located in C drive, use 8 processors to complete the calculation. The name of the file which contain all the parameters for running the simulation is in the file name called as min.conf. Make sure that it is having the same name, and save everything in min.log file. That is what it means. And when you hit enter, now your simulation has begun, my friends. Right. So it has recently created this min.log file. It indicates that the simulation is running. Okay. So now how is that I know that simulation is running? You can see that this this cursor is blinking over here. That indicates that simulation is still running. So you can also check the health of your PC by clicking this Ctrl-Alt-Delete and start your task manager. In task manager, it will give you a kind of idea as to how many processor it is using for time being. We have said, okay, use the 8 processors for my simulation, for my calculation. This value will depend on what is the configuration of your PC. If you have like 20 processors that are available, then maybe you can use P20. Okay, now how is that I will know at the very first place how many processors are there, right? So uske liye you can go to the control panel. We will come to this in a while, and you can simply search for device manager. This device manager will tell you there is a section in a device manager called as processor, and in this processor section it will tell you, okay, this much processors are there in my PC. So as you can count 1, 2, 3, 4, 5, 6, 7, 8. There are 8 processor in my computer. Therefore, I use P8 over here. And if there are 20 to 50, 100 processors which are available with you, then appropriately you can use it over here, right? So since I am using all the 8 processors, my CPU should be, consuming 100% of the computational power, right? That means if the 100% computational power is consumed, that means you are using all of these processors. So this can be confirmed using the task manager. And if you go to this performance, you can see around 93 or 98% of your CPU is being utilized, right? If I might have used P4, that means I would be using only 1, 2, 3, 4 processors out of it. So this will be around, say, some 50% in that case, right? So these are the indication that your simulation is running smoothly, right? And it will take some time. Okay, now it has started populating the intermediate files and everything. Okay, the minimization steps, since we are running only for 6,000 steps of minimization, it won't take much time. We can wait for a while. Okay, so now generally minimization happens in a very short period of time. Okay, it might take 5 or 6 minutes to happen. Okay, now you can see that this minimization simulation is completed. Okay, and it has generated a trajectory file. Okay, and it has generated the min.log file that we have requested. Okay, save everything in this min.log file. Min.log file has been created. If you open it in any text editor, it will kind of show you how the simulation has been conducted. Okay, and this is the log file, and by the end of the log file, it will tell you, okay, everything completed successfully, and it took 216 seconds to complete the simulation. Okay, so 216 seconds, if we convert it into time, seconds to minutes. We'll copy this thing and paste it over here. It took around 3 minutes. Okay, so minimization takes around 3.6 minutes. In the same way, once the minimization is over, you can give the same command and perform heating simulation, right? For performing heating, all you have to do is to change the name of the equilibration, change the name of the configuration file. What is the name of configuration file? It is heat.cunn, and save everything in heat.log. Okay, and hit enter. Now I will kind of show you task manager. I can demonstrate you right away how the performance is. Now you can see the performance is like 13% or something. But when I execute this simulation, the CPU usage will directly jump to say some 100% and just hit enter. Now you can see from like 10 to 20, it has now spiked to 100%. And now you can see that your system, all the processors in your system are being used optimally or at its best possible computational power. Okay, so now it will take 3 hours, I know for sure, in my system. Okay, and after that I will have to wait for 3 hours, then I will begin the equilibration simulation. Let me tell you using the result that I already have. Okay, so if I take out the log files for these are the results. These are the results that I have already obtained. So if I go for heating, there should be something called as heat.log file. Okay, these are the results that we have already obtained. Okay, so heating took 3691 seconds. Okay, so it kind of took an hour, right? इसको 1 घंटा लगेगा. Okay, so you would have to wait for yet another hour in order to complete the simulation for heating. Then you would initiate the simulation for equilibration, and how much time the equilibration will require, I will tell you. Here is the equal.log file. I open it with text editor. At my PC, it took around 792 seconds. So how much time is it? It took 131 minutes. Okay, so divided by 60 and it will be in hours, right? Seconds to it took around 2 hours. And for conducting the production run, let us see the log file for production, how much time it took for completing the production. It took around the same thing, 1 nanosecond simulation, 2 hours. So my friends, if you have a PC with 8 cores of 3 point something gigahertz speed, this complete simulation will take around 2 hours for production, 2 hours for equilibration, 1 hour for 6 or 7 hours it will take. And you don't, you would have to make sure that the simulation will continue to run for that much of amount of time. You would have to make sure that electricity is always there. Okay, so now there is one thing that I would also like to mention, like these are simple simulations. Okay, so the system is small, therefore it took around 7 minutes for minimization, 1 hour for heating. If the size of the system is more, these might take 3 hours, 4 hours even for heating, 7 or 8 hours or even 12 hours for equilibration. And depending on the speed, depending on the size of your system, depending on the duration that you are trying to simulate, it might take even a few days or weeks or even months. So this is very time consuming process, and computationally it is very quite intensive. Therefore you would have to remain patient, and it is necessary that you should have good computational power in order to begin it, okay, at the very first phase. So my friends, if you go this way, like first manually run the minimization simulation, then manually run the heating simulation, then manually run the equilibration, and then production, right? You might have to wait for each and every step like we are waiting now, right? So what I have done is that I have kind of created a pipeline, an automated pipeline, wherein you begin the simulation and it will kind of automatically conduct all the steps like minimization, heating, equilibration and production. You don't have to intervene after every step has been calculated. So how is that you do it? I will tell you. Now I will close this thing. Okay, I will sort by date modify. Okay. I will just to demonstrate you the automation thing, I will remove the files that I have created so far. Okay, now what I have done is that I have created this batch script that will kind of automate everything. Okay, first it will execute the minimization, then it will execute heating, then it will execute equilibration, and then it will execute production. Okay, this is how you use this automation, right? You can simply go to the bar, or you can say you can simply get to the location or address bar and hit CMD. Okay, and just make sure that everything is there. Of course, this is the good strategy always, and you have to call this simulation.bat file. Simply type simulation.bat and hit enter. Now you can see, my friends, it has initiated minimization. When the minimization will be completed in 1 or 2 minutes, it will kind of show you, okay, now it has initiated heating. Then after heating is over, it will tell, okay, it has begin with the equilibration process, and then production. So in this way, you don't have to give command each and every time. But the thing is that the path in this simulation file must be, you should be really very careful while giving the path to the NMD program. Okay. So this is how I have shown you how is that you can even automate the process so that you don't have to be there on terminal every time you run a simulation. Okay. So this is, my friend, how is that you set up the MD simulation, how is that you run the MD simulation. Okay, I hope that you get a kind of feel, okay, this is how you get started at least. Okay, is there any doubt?
Thank you so much, sir, for your valuable time and insightful session. Now the session is open for discussion. Anyone can ask anything. You can turn on your mic or write in the chat box.
Can I stop presenting?
There are any queries?
Okay, I kind of I can get okay, this might be a kind of overdose because there were a lot of new terms and new terminologies. I was I went on talking about this thing, but if you go step by step, follow my YouTube channel, then maybe in a week or so you would get into a better touch of this concept. No, it will not happen just in a single session. You might want to try it out with very patiently. You will have to do these things. I don't expect कि आपको एक ही इसमें सब आ जाएगा.
So we
If you
will share
practice
your
it.
channel link also in the groups.
Huh?
So we will share your YouTube channel link in the groups also.
Yes, sure. If you have any doubt, you can email me. If you have any question that you can ask, okay, you can simply email me and I will respond to you. Okay. So we have run out of time simply in demonstrating how do you get start and execute the MD simulation. I cannot proceed for how do we analyze the system as such. Okay.
Yes.
The final product would be like the configuration as well as the TCD file that will be generated.
Yes. So I
Okay,
think
now
there are no
okay,
queries.
maybe just a minute, just a
Yes,
minute.
sir.
Okay, now you can see that the minimization is over. Now it has started heating, and once the heating is over, it will start equilibration, and after equilibration, it will start production. So in this way, once you initiate this thing, and then maybe you can go have some coffee or do something in your wet lab, whatever experiments that you have planned, and let the computer do its stuff. You don't have to stand there staring at your computer monitor. Okay, when will this finish and when I will or when I will proceed for the next stage. Okay, that's it.
Thank you, sir. Thank you so much, sir. Now I request Ms. Malika Bora to end the meeting with a formal vote of thanks. Thank you to Ms. Malika Bora.
Good afternoon, Good afternoon to everyone present here. On behalf of the college, I extend my heartfelt gratitude to all who have contributed to making today's program a meaningful and successful one. First and foremost, I express my sincere thanks to our respected Principal Dr. Sumit Khadua sir for providing us continuous support, guidance, and encouragement in organizing such events. I would like to extend my deep gratitude to our distinguished resource partner Dr. Mehran sir for taking out valuable time from your busy schedule and sharing your insightful knowledge with us. Your work has truly enriched our understanding. My sincere thanks to our Vice Principal Coordinator for their cooperation and supervision in the conduct of this program. I also acknowledge the valuable assistance of our faculty members who work behind the scenes to ensure that all arrangements were made efficiently. A special thanks to all the participants whose active involvement and enthusiasm make the session interactive and meaningful. Lastly, I thank everyone present here for being a part of this program and for your patience. Thank you. Have a wonderful day.
Thank you, sir. Thank you so much, sir.
Thank you, sir.
Thank you for the kind opportunity and bearing me for last 2 hours. Okay.
Thank you for your time, sir. Thank you, sir.
So one more thing I would like to add here. The feedback link in the chat box was not working. So immediately after we close this meeting, we will post the feedback link in our WhatsApp group. So participants are requested to please fill out the link because it will be active only for 15 minutes. Thank you.
Thank you.
Please share the feedback with me as well. Okay.
Yes.
Sure, sir. Sure.
That it will be it will be kind of scope for me to optimize the presentation for biology community so that it would be more effective. It would be a learning opportunity for me as well.
Your feedbacks are always too good, sir. Yeah, last time also it was too good. That's why we have once again we have invited you. They're really overwhelmed with your presentation.
Okay.
Thank you everyone.
Okay. Shall I leave the meeting?
Yes, sir.
Yes,
Thank you, sir.
yes, sir.